In this class, we're going to consider the power rule for differentiation. So the power rule is generally the first rule that we learn when we start differentiation, and it's probably the rule that you're going to use most. Certainly, initially, it's a rule that you're going to use most. And if you want to be successful in calculus, in differential calculus, you've got to really be pretty good with the power rule. But it's fairly straightforward. And the main challenge really is not using the rule, it's adapting to different scenarios, like in these different example types here, where you apply the rule not in different ways, but in different contexts, different types of function, basically. So we'll have a look at these examples in a moment, but just first of all, thinking about what the rule says. The first thing is that the power rule is good for functions of the form ax to the n. So in reality, a and n are likely to be numbers, as you can kind of see in these examples here, something like this, so 3x to the 5. And the rule basically says, and it's called the power rule, because it says that if this is your function, then the derivative f prime of x, or f dash x, is achieved by multiplying by the power, or bringing the power in front, so that would become n times a, and then reducing the power by 1. So you multiply the power in front, and then you basically take 1 off the power, or reduce the power by 1. So this is technically, I guess, the formula, but we tend to think of it more intuitively than formulaically. So it's just multiply by the power, reduce the power by 1. And you would do that for every single term. So some of these examples have only got one term, but if you've got multiple terms, then you just apply that power rule to each term individually. If the function was given as y, so if it was y equals ax to the n, then we're just going to use the notation dy dx, so derivative of y with respect to x, but we get the same result. There's never any changes in the result when you use these different notations to represent a function and its derivative. The rules, like the power rule in this case, are always the same. Okay, so let's take the idea of multiply by the power, reduce the power by 1, and apply it to these different scenarios, and just see the kind of results we get and see the kind of problems that we're going to maybe run into as well. So this one's fairly straightforward. This is kind of an entry-level question. It's already in the correct format, although the number in front here is just a 1 basically. So when we multiply the power in front, or bring the power in front, it's going to be quite straightforward, because it will just be 4x and reduce the power by 1, take 1 off the power to get 4x cubed. So quite straightforward really. Next one, fairly similar again. We've got a number in front this time, so when you bring the power down, or multiply by the power, you're going to multiply that to the number that's already there. So 3 times 5 is 15, so it'll be 15x. Take 1 off the power, so that goes down to a power of 4. So multiply by the power, again, reduce the power by 1. How many times am I going to say multiply by the power and reduce the power by 1 in this video? Probably another 5 or 6 times. So this guy here, starting to get into like slightly different scenarios now. Remember that if you've got a term with just an x, that really means an x to the power of 1. And normally we don't write in the power of 1, but it's good because we're working with examples of, or an example of a rule that uses the power here. It's good to bear in mind that that is a power of 1, and even sometimes to write it on, just to remind yourself. So if we apply the same rule, the power rule, multiply the power in front, so we get 1 times 2, which is obviously 2, and we reduce the power by 1. I'm just going to write it out this time. It becomes 2x to the power of 0. But from indices rules, we know that anything to the power of 0, regardless of what this x value actually is, anything to the power of 0 is 1. So this is effectively 2 times 1, which is just 2. But that's always going to happen if the term is just an x term, because if it's just an x term, then that means always x to the 1. If you're always reducing that power by 1, because you're using the power rule, that's always going to go down to a power of 0, meaning that that thing to the power of 0 is just the number 1. So effectively with these, the derivative of a function in the form 2x is always just going to be 2. If it was 3x, it's going to be 3. If it was ax, the derivative would just be a. Okay, so that's kind of a special case. You'll see a lot of those, and you don't need to write in this intermediate line here. You can just go straight to f prime of x or f dash x equals 2 or 3 or whatever the number in front is. So recognizing that format will be one of the first kind of little tricks, I guess, that you're going to pick up. Okay, right, so moving on. Slightly different scenario here. Here we've got a constant function. So one way you can think about these, because it is awkward to know how to apply the power rule to these initially, because there's no x term in this and the x term should be there, you can think of it as being an x to the power of 0, because x to the power of 0, as we saw here, is just 1. So this is just a different way of writing what we had originally, which was just 7. This is effectively saying 7 times 1, which is still 7. So taking that idea in mind, or writing it in that way, and then using the power rule, we say, okay, we multiply the power in front and then reduce the power by 1. But if we multiply the power in front, we're going to get 0 times 7, which is 0, multiplied to x to the power of minus 1. But 0 times anything is just 0. So this just comes out to be 0. So if you've got a constant function, in other words, if you've got just a number, any number, and you're trying to differentiate it, the derivative will always be 0. When you get further into calculus, you're going to realize some other ways to think about that, and you're going to realize other ways to know why that comes out to be 0. But for the time being, just basically remember that rule. So we've seen a few variations already. We've got these guys that are in the fairly consistent format with the power rule general format. We can apply the rule. When you've got a format of ax, then the derivative is just a. When you've got a format of just a constant, because remember this started off life just as the number 7, the derivative will always be 0. If this was a 5, it would be 0. If this was a million, it would be 0. Okay, so you get the point. Okay, right, so let's look at a few other variations. This guy has got a couple of things going on that's different. The first is that we've got a negative power here, but that doesn't stop us using the power rule, okay? We just use it in the same way. The second thing is the fact that we've got more than one term, but like I said earlier, if you've got multiple terms, you just differentiate them term by term, okay? We've also, I suppose, got the different notation here. So we're going to represent our derivative using dy dx, so derivative of y with respect to x. Okay, so we're going to get dy dx equal, so multiply the power in front, so it's minus 2 times 3, which is negative 6, x to the power of minus 3, because we're taking 1 off the power, we're going down by 1, so it's minus 2 minus another 1 to give you negative 3. The second term's a little easier, it's kind of directly in this sort of format here. So 5 times 2 is 10, reduce the power by 1, that becomes x to the power of 1, so we could just leave it like that. Now you might, if you get negative powers, want to consider rewriting them with a positive power, so you could rewrite that as negative 6 over x cubed using indices or exponent rules, and that might not be useful initially, but later on in these questions you're going to start substituting numbers in for x to do various things using the derivative, and it would be more useful generally to have a positive power than having a negative power. So that's quite a common scenario with derivatives. Okay, so let's have a look at the next guy. So this doesn't quite match up with this format because literally we need number x and then a power. The power can be negative, this number can be negative as well, but this does not accommodate a fraction. So this is basically not in what we would call a differentiable form. We need to put it in a differentiable form before we can differentiate. Now, the big mistake the students will make here, because they don't have experience yet, is to put it into a differentiable form, but think that is already the derivative. So you've got to be careful with that. Basically, it means we need a line of work in here before we take our derivative, just to get it into a differentiable form. Then we can take our derivative. So in this case, using exponent rules, we can make, it's actually the reverse of this rule here. We can bring this x to the power of 3 to the top of our fraction. Let's actually use another number. Let's use a 4 just to make it a little different from this example. So if we bring that x to the 4 to the top, it becomes an x to the negative 4. And we could just think of this 1 over 2 as the number 1/2 in front of that x term. So it becomes 1/2 x to the minus 4, okay? Just using exponent rules. Now this is in a differentiable form. This is ax to the n, so the a value is 1/2, the n value is negative 4, so we're ready to take the derivative using the power rule. So dy dx, derivative of y with respect to x, that's going to be 1/2 times minus 4, which is negative 2x, taking 1 off the power, remember, so it goes down to a negative 5. It's also a common mistake initially when you're doing derivatives to take 1 off the power but write it as minus 3. I don't know why, just because negative numbers are a bit confusing sometimes. But yeah, this would be the derivative. And again, we could rewrite that with a positive power as negative 2 over x to the 5. It's good practice actually to, even though your focus initially will be on the rule, to take that extra line of work in just to write them with positive powers, because you probably will need to do that before too long. Okay, right, so let's check out the final example. Slightly different scenario, but again, not in a differentiable form. There's nothing in the power rule to accommodate a square root, or indeed any other kind of root, a cube root or a fourth root or anything like this. So we need again to turn to indices rules, exponent rules. There's a lot of use of those rules in calculus because a lot of the calculus rules themselves relate to powers. And if things are not in the correct format, then we need to manipulate them using exponent rules to get them in the correct format. So again, this is not in a differentiable form, but the exponent rules tell us that a square root is the same as a 1/2 power. So we can change this to x to the 1/2, which is now in a differentiable form. Your n value, your power, can be a fraction, and in fact, you'll see a lot of fractional powers in calculus and in differentiation. So they can be awkward at first, you'll get used to them fairly quickly. So now this is in a differentiable form, so we can take our derivative, so dy dx equals, and just applying the same rule even though it is a fraction, so multiply by the power, or bring the power in front, so it's 1 over 2, x, reduce the power by 1, so we're taking 1 off of 1/2. 1/2 minus 1 is minus 1/2, so it's going to be minus 1/2. These guys can be a little confusing at first when you've got fractional powers. This can get more difficult. Say this was like a 3 over 2 or some more awkward fraction. It might take you a little while, depending on how good you are with fractions, it might take you a little while to get used to taking 1 off those types of numbers, reducing them by 1, but you'll adapt to those fairly quickly because it is quite a common question type. So again, we could tidy this one up. I mean, this is a derivative at this point. We could tidy it up by rewriting it in a more compact form. In this case, we could bring the 2 down to the bottom of the fraction as well and make it 1 over 2x to the power of positive 1/2. We could even go as far as writing that as 1 over 2 root x, because this half power on the bottom of the fraction is the same as a square root, just using that kind of rule that we used there. So that is the power rule for differentiation. It's a very, very important rule. You'll use it a lot, especially when you're just starting differentiation. Learn the formula if you wish, but learn more by practicing the questions, just how to use the rule in its kind of native primary form, but then all of these variations. This is really where you want to focus. Challenge yourself with questions that are not in differentiable forms, because in reality, it's likely that any test or homework assignment or exam or anything you take where you're being assessed on the power rule is not going to just give you nice tidy formats that match in really closely with the rule. You're likely to see questions in different formats because that's what you're going to want to be tested on. So do challenge yourself and try to get used to all these different variations. There's infinitely many different variations. You could see multiple terms here. You could have terms that have got square roots and then a kind of normal term, a polynomial type term, and then, you know, some other square root, all sorts of variations. But do challenge yourself with those. Adapt into the different scenarios and the different types of function that you've got to differentiate is really the key to being good with the power rule. So hopefully that makes sense. I think the rule is fairly straightforward, but adapting to these different scenarios is probably going to be your primary challenge. Once you've got this rule down though, and do spend some time making sure you are completely comfortable with this rule before you move on, but once you do get it down, move on to the next rule that we're going to look at, which is the product rule.